Welcome to the second lecture of the course Atomic and Molecular Physics. In the previous lectures, we have studied about the postulates of Bohr's theory, and in the postulate, after the postulates, we have find the expression for the radius of Bohr's orbit. Also, we have found the expression for velocity of electron in a nth Bohr orbit, and also we express the energy of the nth Bohr orbit in the previous lecture. Now in this lecture we are going to study the origin of line spectrum, how the line spectrum originates from the transition of the electron. That study will carry over in this lecture. Also we will study how the Rydeberg constant varies due to the finite nuclear mass, how that variation takes place, that we will study in this lecture. And also we will study about a different spectral series that arises from the transition of the electron in a hydrogen atom. In the today's lecture, our learning objectives will to understand the origin of the spectral lines and to study the different spectral series in hydrogen atom. And also we will find the series limit for each particular series in the hydrogen spectrum. So let's start with the origin of spectral series. Now in the previous lecture we have studied that according to the third postulates of Bohr's theory, that the quantum of energy will be radiated when there is a transition of the electron from higher energy level to the lower energy level takes place, and that quantum of the radiation will have the energy which is equals to the difference between the two energy levels. So here you can see that we have h nu equals to ei minus ef, where nu is the frequency of the emitted radiation, h is the universal Planck's constant, and ei is the energy of the upper level, that is the energy in which the electron is initially situated, and the ef is the energy of the lower energy level, which is the final energy levels at which electron jumps from a higher energy. So the difference between the energy will be equals to the energy of any radiated quantum of energy, that is the radiation emitted out of that transition of the electron. So we have expressed in the previous lecture the total energy as En is equals to minus z square me power 4 divided by 8 epsilon 0 square n square h square. Now in this expression you can observe that here the energy is inversely proportional to n square, and the negative sign indicates that the electron is bound to the nucleus. So I can express the energy of the upper level, that is the initial level, whose principal quantum number is Ni, as Ei. So Ei will be equals to minus z square me power 4 divided by 8 epsilon 0 square Ni square h square, where Ni is the principal quantum number for the energy which has a for the energy level which have a energy Ei. And also I can write Ef, which is the energy of the final energy level at which electron jumps. So it is a lower energy level. So Ef equals to minus z square me power 4 divided by 8 epsilon 0 square nf square h square. And now we know that from the Bohr's third postulate that h nu equals to ei minus ef, that equation will become h nu equals to minus z square me power 4 divided by 8 epsilon 0 square ni square h square minus z square me power 4 8 epsilon 0 square nf square h square, and that difference finally will give rise to the expression as h nu equals to z square me power 4 divided by 8 epsilon 0 square h square, and in bracket we will have 1 by nf square minus 1 by ni square, which you can see in equation number 3. So here I can write this h nu in equation 3 as hc by lambda, because we know that the speed of light we can write as a product of frequency and the wavelength of the light. So by using the expression c equals to nu lambda, I can write this h nu as hc by lambda. So I will get hc by lambda equals to z square me power 4 divided by 8 epsilon 0 square h square, and in bracket we will have 1 by nf square minus 1 by ni square, and so I will get 1 by lambda equals to z square me power 4. This hc will be in the denominator, and that will give rise to a 8 epsilon 0 square ch cube in bracket 1 by nf square minus 1 by ni square. Now the quantity here 1 by lambda is known as the wave number, and which is represented by the nu bar. Now wave number gives the number of, here the wave number which is 1 by lambda, that gives us the number of waves per unit length, and its unit is per centimeter or per meter, and that's why we will get nu bar equals to z square into r infinity in bracket 1 by nf square minus 1 by ni square. Now here r is called as the Rydeberg constant, and the suffix infinity indicates that this Rydeberg constant we have evaluated under the assumption that the mass of the nucleus is infinite, and that's why the nucleus is at rest and only the electron moves in that system, that is in that atom. So here we are considering the nucleus of heavy mass which is infinite mass, and that's why the suffix infinity is there. So r infinity is the Rydeberg constant, and you can observe that we have r infinity equals to me power 4 8 epsilon 0 square ch cube. Here m is the mass of electron, e is the charge on electron, epsilon 0 is the permittivity of free space, c is the speed of light in vacuum, and h is the universal constant which is a Planck's constant. And by substituting all those values, all those fundamental constants, I will get r infinity as 1.097 into 10 raised to minus 7 per meter, or in the case of if we use the unit as per centimeter, then we will get r infinity equals to 109,737 per centimeter. Now this r infinity is a constant for all atoms, and so if you read the equation 4, so by substituting this value of r infinity in equation number 3 here, I will get h nu equals to, now this me power 4 8 epsilon 0 square h square into ch is there, that is a Rydeberg's constant. So if I substitute the value of Rydeberg's constant in the equation 3, I will get equation 3 as a equation 5, that is h nu equals to z square ch into r infinity 1 by nf square minus 1 by ni square. So equation 5 gives us the energy of a quanta in terms of the Rydeberg constant. So now let's study about the Rydeberg constant in more detail. So here we will study variation in Rydeberg constant due to a finite nuclear mass. Now whenever the nucleus has a finite mass, so generally the nucleus does not have an infinite mass. It is a very large compared to the electron, but in reality it has a finite mass. So due to the finite mass of the nucleus, the value of Rydeberg constant, there is a slight deviation in that value, and we have the formula for the Rydeberg constant under the assumption that a nucleus has an infinite mass as r infinity equals to me power 4 divided by 8 epsilon 0 square Ch cube. And for an atom having a finite mass, having a nucleus of mass capital M, is I can write for that nucleus the Rydeberg constant as Rm, suffix m stands for nucleus of mass M, equals to mu e power 4 divided by 8 epsilon 0 square Ch cube. Now you can compare both this equation for R infinity and Rm, and you will observe that instead of mass small m, we have here a mu. Here mu stands for the reduced mass of the system, that is the reduced mass of the nucleus and the electron. So reduced mass of the nucleus and the electron constitutes some finite value. Now we know that the reduced mass is given by reduced mass of the electron and the nucleus system is given by small m times capital M, that is mass of electron times mass of nucleus divided by small m plus capital M, and which is nothing but the small m divided by 1 plus small m by capital M. So this is the value of mu, and if we substitute this reduced mass in the equation 6, I will get, in equation 7 I will get Rm equals to me power 4 8 epsilon 0 square Ch cube into 1 by 1 plus small m by capital M. Now this me power 4 8 epsilon 0 square Ch cube is nothing but the R infinity, so we will get Rm equals to R infinity divided by 1 plus small m by capital M, and this is equation number 8, and from that equation you can observe that the Rm, that is Rydeberg constant for nucleus having a finite mass, is less than R infinity, that is the Rydeberg constant for nucleus under the assumption that it has infinite mass is less by a factor 1 by 1 plus small m by capital M. So Rm is less than R infinity, and the value of Rm is depend on the mass capital M, or you can say it depends on the mass mu. So it is different for different systems, different atoms, and we know that R infinity is a constant for all atoms, but this Rm is different for all different atoms because they have a different reduced mass. Now let's calculate the Rydeberg constant for hydrogen atom. So we have the formula for Rydeberg constant for any nucleus having a finite mass as Rm equals to R infinity divided by 1 plus small m by capital M. Now here for the hydrogen atom, you can observe that the Rydeberg constant for hydrogen atom R suffix H equals to R infinity by 1 plus small m by capital MH. Now here small m is the mass of electron, and MH suffix M suffix H stands for the mass of a hydrogen atom nucleus. So generally the ratio of mass of the electron to the mass of proton, because the hydrogen atom consists of a single proton, that nucleus consists of a single proton, so that ratio is a small m by capital M is generally 1 by 1836. So mass of the nucleus here is 1836 times larger than the mass of electron, and therefore the Rydeberg constant for hydrogen atom is less than the R infinity by about 2000 times. So the Rydeberg constant for a hydrogen atom will be 109677 per centimeter, whereas R infinity has a value 109737 per centimeter. Similarly, we can find the Rydeberg constant for helium atom. Here we have to just substitute the mass of the helium nucleus. Okay, by using equation 10, you can find the Rydeberg constant for helium atom. Now let's study the different series that arises due to the transition of electron in a hydrogen atom. So basically we study these 5 series which are more fundamental. So first series is a Lyman series, second series is a Balmer series, third series is a Paschen series, fourth one is a bracket, and fifth one is a Pfund series. So let's study these series in details. So let's study about the first series, which is a Lyman series. Now Lyman series exists when there is a transition of electron from the initial energy level, which corresponds to Ni equals to 2, 3, 4, 5 and so on, to the final energy level, which corresponds to N equals to 2, which corresponds to N equals to 1. So here you can observe that in the diagram we have shown the transition from Ni equals to 2, 3, 4 to the Nf equals to 1. So whenever this transition takes place, whatever the series arises here is the Lyman series. And for the Lyman series we have the wave number. I can write, we have the formula for the wave number as 1 by lambda equals to R times 1 by Nf square minus 1 by Ni square. So here if I substitute the value of Nf as a 1, we will get the wave number for the Lyman series as a 1 by lambda equals to R into 1 minus 1 by Ni square. Now we have to find the series limit for the Lyman series. So to find the series limit for Lyman series, we have to find the minimum and maximum wavelength for this series. To find the maximum wavelength, we have to select here Ni equals to 2, because for that transition the energy will be minimum and the wavelength will be maximum. So by substituting the value of Ni equals to 2, we will get lambda as a lambda max. So I can write the equation for a wave number as 1 by lambda max equals to R times 1 minus 1 by 4, which comes out to be 3R by 4. And from this result you can find the maximum wavelength for the Lyman series. And to find the minimum wavelength for the Lyman series, we have to substitute Ni equals to infinity. By substituting the value of Ni as a infinity, we will get minimum wavelength for this transition. This will be the minimum wavelength and the energy will be maximum for this transition. So 1 by lambda minimum will be equals to R times 1 by 1 minus infinity, which is just R. So you can observe that the Lyman series, the wavelength of the Lyman series lies in between 3R by 4 to the R. Here R is the Rydeberg constant. And this wavelength, if you calculate, you will find that the wavelength will lies in the ultraviolet region of the electromagnetic spectrum. The second series is the Balmer series. Now this Balmer series exists when there is a transition of electron from Ni equals to 3, 4, 5 to the Nf equals to 1. Here the final energy level, that is the lower energy level, corresponds to Nf equals to 2. So whenever the electron jumps from the higher energy level to the final energy level, which corresponds to Nf equals to 2, we will have a Balmer series. Now here you can observe that for a Balmer series, if I substitute the value of Nf as a 2, I will get 1 by lambda equals to R infinity times 1 by 4 minus 1 by Ni square. And by using this equation I can find the minimum and maximum wavelength for the Balmer series. To find the maximum wavelength for the Balmer series, I have to substitute here Ni equals to 3, and by substituting the value of Ni as a 3, I will get 1 by lambda max equals to R times 1 by 4 minus 1 by 9, which comes out to be 5R by 36. And to find the minimum wavelength, I have to substitute here Ni equals to infinity, and you will get 1 by lambda equals to R into 1 by 4 minus 1 by infinity, which comes out to be R by 4. So here you can observe that the wavelength for the Balmer series lies in between 5R by 36 to the R by 4, and this wavelength results in the visible region. So this is the visible, it comes in the visible region of the electromagnetic spectrum. So Balmer series was the first series which is observed, and it comes in the visible region of the electromagnetic spectrum. Now the third series, which is a Paschen series, it exists when there is a transition of electron from initial energy level, which corresponds to Ni equals to 456, to the final energy level corresponding to Nf equals to 3. And so I will get the wave number for the Paschen series as 1 by lambda equals to R times 1 by 9 minus 1 by Ni square, which comes out to be equation number 13. And if you want to find the series limit for Paschen series, we have to just substitute here Ni equals to 4, which will give me the maximum wavelength of Paschen series. By substituting Ni equals to 4, I will get 1 by lambda max equals to 7R by 144. And for minimum wavelength, we have to substitute here Ni equals to infinity, which will give me 1 by lambda minimum equals to R by 9. So you can observe that the wavelength of the Paschen series lies in between 7R by 144 and R by 9, and this wavelength comes in the near infrared region of the electromagnetic radiation. The fourth series is a bracket series. Now bracket series exists when there is a transition of an electron from initial energy level corresponds to Ni equals to 567 to the final energy level corresponding to Nf equals to 4. And here, by using the formula for wave number, I can find the wave number for the Paschen series. By substituting the value Nf equals to 4, I will get 1 by lambda equals to R into 1 by 16 minus 1 by Ni square. Here also we can find the series limit. By substituting the value of Ni as a 5, I will get the maximum wavelength for the bracket series, and here the equation 14 will become 1 by lambda max equals to R into 1 by 16 minus 1 by 25, which comes out to be 9R by 400. Similarly, we can find the minimum wavelength for the bracket series. By substituting Ni equals to infinity, I will get 1 by lambda minimum equals to R by 16. And so you can observe that the wavelength of the bracket series lies in between 9R by 400 to the R by 16. And if you evaluate this, the wavelength of the bracket series will be in the infrared region of the electromagnetic radiation. The last series is a Pfund series. Now the Pfund series exists when there is a transition of electron from initial energy level corresponding to 6, 7, 8 to the final energy level correspond to Nf equals to 5. So whenever electron jumps from higher energy level to the lower energy level, which has the n value as a 5, we will get a Pfund series in the hydrogen atom spectrum. So by using the equation for a wave number, I can substitute here Nf equals to 5 for Pfund series, and we will get 1 by lambda equals to R times 1 by 25 minus 1 by Ni square. So this equation 15 is the equation for wave number for Pfund series. So here we can find the lower and higher range of the wavelength for the Pfund series. So to find the lambda max, we have to substitute here Ni equals to 6. This level will correspond to the minimum energy and maximum wavelength. By substituting here Ni equals to 6, I will get 1 by lambda max as R times 1 by 25 minus 1 by 36, and that comes out to be 11R by 900. And to find the minimum wavelength of the Pfund series, we have to substitute here Ni equals to infinity. So for that, I will get 1 by lambda minimum equals to R by 25. So this region, this Pfund series lies in the infrared region of the electromagnetic radiation, and its wavelength lies between 11 R by 900 to the R by 25. So these are the 5 series which arises in the hydrogen atom spectrum due to the transition of electron. And these are the theoretical results for the wavelength of the various series and series limits of the various series. Now let's do some assignments. So student have to solve following assignments. So first question is, find the Rydeberg constant for helium atom. So student here have to find the Rydeberg constant for helium atom. We have just seen the formula for how to calculate the Rydeberg constant for various atoms. So by substituting there the mass of nucleus of helium atom, you can find the Rydeberg constant for helium atom. And second question, student have to solve that they have to find the wave numbers for Balmer series for initial energy level corresponds to Ni equals to 456. So here you have to find the wave numbers by using the formula of wave numbers. For Balmer series, remember that NF equals to 3. Now let me recapitulate what we have seen in this lecture. Here we have seen the energy of spectral line, the formula for energy of spectral line in hydrogen atom, which is given by h nu equals to z square ch r infinity in bracket 1 by nf square minus 1 by ni square. And the term value that is a wave number, here the term value indicates the wave number. If you divide this energy h nu by ch, you will get the term value, which comes out to be nu bar equals to z square r infinity 1 by nf square minus 1 by ni square. And we have also seen the Rydeberg constant for infinitely heavy nucleus, that is the assumption that a nucleus has an infinite mass. We get r infinity, Rydeberg constant for infinite mass nucleus, as a me power 4 divided by 8 epsilon 0 square ch cube, and which comes out to be 1.097 into 10 raised to plus 7 actually per meter. Rydeberg constant for an atom having a nucleus of a finite mass capital M. So if you consider the nucleus has a finite mass, not an infinite mass, then in that real situation the Rydeberg constant for that nucleus Rm will be me power 4 8 epsilon 0 square ch cube into 1 by 1 plus small m by capital M. Here small m is the mass of electron and capital M is the mass of the nucleus, and which comes out to be r infinity by 1 plus small m by capital M. So the Rydeberg constant for the atoms will be less than r infinity by a factor of 1 plus small m by capital M. Also in this today's lecture we have seen various series. So you have to remember here that for Lyman series Ni is 2, 3, 4 and Nf is 1. For Balmer series Ni is 3, 4, 5 and Nf is 2. For Paschen series Ni is 4, 5, 6 and Nf is 3. For bracket series Ni is 5, 6, 7 and Nf is 4. And for Pfund series Ni is 6, 7, 8 and Nf equals to 5. In the upcoming lecture we will study about the quantum numbers. Basically we will study principal quantum numbers, orbital quantum numbers, magnetic orbital quantum number, spin quantum number, magnetic spin quantum number and total orbital angular momentum quantum number in the upcoming lecture. So this is it for today. Thank you very much.